So guys, anybody have any questions? I had a couple of really good questions in office hours. Anyone else have any other questions from homework stuff? Remember what's happening tonight, by the way?
Quiz.
Quiz! And what's that quiz cover?
6-1 to 6-4.
Yes, that's right. So does anyone realize what that means is not on the quiz? 6-5 is where we learned properties of logarithms. So that's not on the quiz. Just like basics of logs, basics of exponentials, graphing them, some shifting stuff. You know, doing some basic log evaluation, like log base 2 of 8, stuff like that. Okay.
Can we go over 6.4, a question like number 54?
Yeah, let me see. Oh, okay. All right, so I showed you how to do this kind of thing in your calculator. So let's do this. Let me pull up my calculator. So what's going to happen is you're going to put one side of this equation into y1 in your calculator, and you're going to put the other side into y2. You could also use Desmos. Desmos would do this also. So let's look at the calculator. So let me pull the calculator up. We'll make a different equation here. So let me see, where is it safe to write here? Hold on. Scheisse on my side. There we go. All right, so let's make another equation real quick. Where can I write it? All right, I'll write it up here. So let's say I've got, can you guys see up there? The little 2 up here?
Yes.
Okay, so let's say 2 log of 4x minus 1. Oh, shit. Let's see. I'm going to try to make it have an answer. Let's see if I can do that. All right. Log. Let's do this. Sorry. Natural log of yeah, that should work. Let's find out. Equals natural log of 3x. All right. Last time I tried to do this, it didn't work so well. So let's find out. So is everybody able to see that? So 2 log 4x minus 1 equals natural log of 3x. Do you guys understand if there is a way to solve that by hand, it will not be easy. Oh, shit. Poor little natural log. Because I've got 2 logs in this equation. They have completely different bases. Could you please show how to find the x and y? Oh, okay. Yeah, just a minute. All right, so let's put this in the calculator. So what I'm going to do is I'm going to take one side and I'm going to put it into y1. So let me put 2 log 4x minus 1. And I'm going to put the other side, natural log of 3x. And let's see if Jeff made something that makes any sense. I'm going to do zoom 6. I almost always do zoom 6 because I don't know what kind of weird shit I did to my window before. So if I always do zoom 6, it takes me back to a 10 by 10. Uh-oh, Jeff. Oh, crap. Let's see. All right. I think I can fix this. All right. This does not look, this looks almost like red is all, okay. So do this favor for me. Let me make, again, I made this problem. Let me change the problem a little bit. Let me make, let me see. All right. So let me make this, this kind of sucks, Jeff. That's too bad. If I make that -1, all right, if this doesn't work, I'll have to pull a problem out of the book. I don't want to sit here all day trying to make a good problem. -1, let's see what that does. All right, so now it's got a definite answer down here. See that? That's what you're looking for, right? Does that make sense? Because you want to see where that line equals that, where, you know, that curve equals that curve. So does anyone remember what's one thing I could do? Because that's really messy. How can I look at that better? How can I get
Zoom
a better
box.
zoom box? I love it. So zoom is like the enhance on those fake crime things. So now I'm just going to make it a little bit bigger. I'm going to keep my axes to show up. I could just hold the button down and go, wee-ha. All right. All right, so now if I hit enter, I'm just going to zoom in on that. And look at that. Look how beautiful that is. All right. So I could trace, but trace doesn't give me the exact answer. See how it bounces? It's somewhere in between those two. So what do? How do I get the answer?
Calculate intersect.
Yeah, so hit second trace. I want to calculate. Everything up on this top row is graphical stuff. The graph button, giving that away. But everything up here is to do graphic. So what calc means calculate something graphically. All right, so I want to calculate the intersection graphically. So I went over the steps here, and the last thing I said was, if you put your cursor right on the answer, hit enter, enter, enter. There you go. That's the answer to that equation. There's a math class called Numerical Methods. Doesn't that sound inviting? Where you learn the actual algorithms the calculator uses to solve this equation, and then you can do it by hand to a degree, you know. Anyway, all right. A little plug for that. Is that okay? Okay. Anything else, guys? Anything? Oh, yeah, there was somebody asking about finding the X and Y intercept. So let me see. Blah, 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 blah. Let me find a decent problem. Here we go. All right. So there's this little section in the homework. So tell me, does the way that you find X and Y intercepts depend on the function itself? No. How do I find the X intercept? What do I do?
Y equal to 0.
Yeah, set Y equal to 0. And how do I find the Y intercept?
X equal to 0.
Holy shit, right? And of course that has to do with the fact that the X intercept is on the X axis, and what is true on the X axis? Y is 0, because it didn't go up and it hasn't gone down. It's right on the ground. So that's why it makes sense. So if I do, like, for example, number 22, where is Y in this equation?
F of X.
Good. So if I set Y equal to 0, what do I get when I try to solve this? What do I have to do to solve this? I've got to subtract 3. Is there anything wrong with what I've just written down in terms of solving it? You guys cool with this so far? Good, good. Now, how do I rewrite? Is everybody, I really want to make sure you guys are okay with what just happened. This is all I have to do ever, whatever the function is. Do you guys remember when I told you in one of my last math classes, I had an equation that had about 14 variables in it, and I had to find the W-intercept. What did I do? I made all the other letters 0. Isn't that sweet? I don't give a shit how many dimensions you're in to find the intercept for one axis, maybe one of 80 axes. To find that intercept, you make all the other letters 0. Isn't that beautiful? The idea doesn't give a shit how many dimensions you're in. And that's just a cool sentence to say, right? My idea doesn't matter how many dimensions I'm in. So how do I rewrite this logarithm? What's the base on this logarithm?
10.
10. So 10 to the negative 3 equals 5x plus 10. And you know, that's not the prettiest number. I don't care. That's easy. Is that cool? Just solve that for x now. No big deal. That'll be your x-intercept. Is that okay? I don't actually care anymore. It's gotten boring now because it's just subtract and divide by 5, blah. And then you set, and this is the nice one, you set x equal to 0. So you just get this. What's log 10? Dadgummit.
It's 1.
I have so much trouble with the number 3. Yes, log 10 is 1. Okay, that was fine, Jeff. Your original 3 was fine. Good Lord. So then the y-intercept is 0 because when x is 0, the output is 4. Jeff put the comma in the right place. That looks like somebody. All right. And when x is 0, I'll get whatever the shit I get there. I'm sorry, when y is 0. So this will be whatever the shit, comma 0. Is that okay? Is that all right? So there are processes, mathematical processes. Finding intercepts is one of them. They don't give a shit what the specifics are. They start with the same idea. Now, so here, this idea doesn't change. This idea doesn't change. The minute I write down what it means, now I worry about what the function is because now I have to solve the damn thing, right? Okay, cool. Thank you. Anything else, guys? Anything else from homework? I think I almost graded everybody's stuff through 6.4. Unless there was some late stuff from early in 6. I might have not gotten to that. Okay. Okay, all right. So if there's no other questions, we're going to get back into, well, not get back into, we're going to do section 6-7. We're going to take a little sneak peek into chapter 7, and then we'll call it a night. Okay, let me get there. Boom. So let me ask you this. This is kind of some cool shit we're about to get into. There's a little something I want to talk about. Let me turn my dragon off. Blobfish, no blobfish, got it. All right. So, let me ask you guys, anybody ever heard of Half-Life? When I say Half-Life, what do you think?
The Valve video game?
See, I was wondering, how many people don't think of a video game? How many people think of something else when I say Half-Life? What do you think of?
The half-life of a chemical or a substance.
Yeah, half-life of like uranium, something radioactive, right? But there is Half-Life the game, right? And it's kind of funny. I've never actually played Half-Life, to be honest. But anyway, we're going to start with something that's actually sort of the opposite of Half-Life. So if I told you, have you guys ever heard of, would you rather me give you $500,000 right now, or I give you a penny and tomorrow I give you double that, and the next day I give you double that for 30 days? Have you ever heard of that before? Which one would you rather get?
1 cent.
Sorry?
The penny.
You'd rather go the pennies if you know anything, yes. Because if you double something over and over again, it gets really big really fast. Ting, yes. What's up? Sorry. Did you have your hand up for a reason? No? Okay.
Yeah, I misclicked.
Oh, you're sorry?
I misclicked.
Oh, okay, you're fine. So if I have, now the problem with that, well, it's not a problem. Let's talk about that by itself. How would I write an equation that represents doubling? So like t equal, I don't know, we'll say 0. I've got 1 penny. T equals 1 day. I've got 2 pennies, right? T equals 2 days. I got 4 pennies. Can somebody figure out how do I write that in equation form? Stay there. How the hell would I write that in equation form? What does doubling mean?
And exponential growth, like
Okay, good. It's the exponential growth. Exactly. It's multiplying by 2 over and over and over again. So at the beginning, you haven't multiplied by anything yet. And then you multiply that thing by 2. So you start at 1 and you multiply it by 2. How many times?
t times.
T times. Right? So I'll say the amount at some time is the 1 penny I started with times 2 to the however many days later. Right? Now, to be honest, I sort of made, I don't know if you realized I was having trouble with how do I want to do this, because this doesn't really necessarily make sense. This is the first day and this is the second day. So what would the 30th day be? What would
29.
29. I like it. So that's a little bit. So how many pennies would they be giving me on the 29th day? I don't know why I'm writing the 1. I don't need you. 2 to the 29th. Can somebody, what is 2 to the 29th? Something excessively interesting.
A really big number.
Yeah, so let me write it down. 536 8709
And 12.
12. That's cents. So to make it dollars, I just do this. So we're talking about how much money are we talking about? We're talking about 5 million. And that's not even all the money you get, because the day before, how many pennies did I give you?
Half that.
Half of that. I love it. 2 to the 28th. I love it, which is half of that. So you don't just get 5 million, you get plus 2.5 million and plus half of that and plus half of that all the way back to the first day. So my offer of 500,000 immediately was chump change, right? Okay, I like it. Of course, you know, you got to carry all these pennies in your pockets, but that's all right. So the problem with this is this an example of continuous growth? It's not a problem. It's not really a problem, but is this continuous growth? How many pennies do I have at half a day? Does it follow? Does this formula work for that?
No.
No, half a day I'm going to have 1 penny, right? Because it's not the second day yet. So I haven't gotten the next penny yet. So it grows incrementally. It's what we call a step function. I have 1 penny, then I have 2 pennies, then I have 4 pennies, right? And so forth. All right, so that's, all right. So what I want to try to get at here, I'm not trying to make this more complicated. It's just that this function, the domain would actually be whole numbers for that particular, we're not going to talk about half pennies. We're not in England, right? We get half pennies and so forth. Okay. Now, what's an example of a problem where the doubling actually is continuous? Maybe something like this. Here's one example. So let's say we're off the coast of Florida. Lake Okeechobee. This is Florida after the ice has melted some more, right? And let's say that there's an Exxon boat, really big boat, and it has a leak. And the leak is growing. Yeah, their boat. The boat's gone now. The leak is growing in area. Every day it doubles. Let's say I guess the boat's still here. Come here, boat. You got to still be leaking. Let's say every week, the area of the leak, of the spill, doubles. Now, is this continuous growth? Yes, because you don't go a whole week and then the start of the next week it goes boom, right? No, it's continuously. It's just like you have to wait a week and now it's got an area twice of what it had before. You guys with me? Okay, maybe. All right. This formula would still work for this, but now I could plug in and it would make sense. any number I want to between 0 and something, right? For as long as the function works. At some point, the function's not going to work anymore. It's not going to do this forever. It's not going to take over the world. Blah. Okay, but this is where things get really neat. So let me ask you, you guys are going to help me. Let's see, what's a good way to do this? Yes. So let's say this area is in, it doesn't really matter what units it is. Who cares? I don't care. I don't want to think about it. I don't know what it would be. I still want to make it something. So let's just make it, sure, square meters. It's a small boat. I don't care. Whatever. Units don't matter. We're shit. Okay. Can somebody tell me what's the area? So we got the area. So normally this means amount. So we can just call it the area. It's fine. Is let's say originally it's 1 square meter. Same way. Times 2 to the t. So that still works. Right. So originally, so a of 0 would be 1. So originally it's 1 square meter at the beginning. So can somebody tell me what's the area 1 day later? Jeff, you can do it. That's easy, right? What's the area after 1 day?
2.
Say it.
2.
2. Okay. 2 square meters. Stay with me. This is so cool. You gotta trust me. This is so flippin'. I just made up a new word for you. Flippin'. It's flippin' cool. Okay. What's the area after 1.1 days? We couldn't do that over there with this shit. I can't say, well, how many pennies do I have after 1.1 days? That makes shit sense. But here I can do, what's the area after 1.1, I'm sorry, weeks. Forgot this was weeks. After 1.1 weeks, what's the area now?
$2.1.
I don't think so, but let's see. When you plug 1.1 into the equation, 2 to the 1.1, is that what you get? 2 to the 1.1. Well, roughly, you kind of round it a little too much. Let's not round it too much, right? 2 to the 1.1, I get 2 let's go out this far, 1435. You'll see why here in a bit. You guys with me? Stay with me, please. Let me tell you this. We are investigating an idea right now. We're not looking at what you're going to have to do in homework yet. Everybody with me? We're just investigating an idea. I'm going to tie it to what you're going to have to know, and everything's going to be great, right? Just don't look at my Florida. It's been through a lot. Now watch this. I'm going to take our pennies away. Our pennies are pennies. Get out of here. Although they did come out to $5 million, but how much? What's the rate of change at this point? Oh, you're going to love this shit. You ready? What's the rate of change in the area so far? Well, how much did the area change from 1 week to 1.1 weeks? How much did it change by? That much, right? Because it was 2 and now it's 2.1435. This should have been days because it's not growing for, it doesn't matter, Jeff. You're fine. It doesn't, units don't matter. And then, so the rate of change would be the amount that the area changed divided by the amount that the time changed. Is that cool? Because rate of change is the slope. Is everybody with me? So it's the outputs divided by, the difference in the outputs divided by the difference of the inputs. Okay. By the way, this is not going to be in this section. This is something we talked about before. Trying to make a connection. Help me out. What's that?
2.
Huh? No. Somebody help. What do you guys get? Help.
1.4.
Yeah, 1.435. So using the calculator actually makes this worse. That minus that is 0.1435 divided by 0.1 is 10 times is 1.435. It's easier to do it without the calculator. No, keep going, keep going. This is going to be so cool. I hope. I don't know. I don't know if you guys are going to be fascinated by this or not. I don't know. So what about if we, now watch this. What if I do, what's the area after, so the area after 1 day was 2 square meters. What's the area after 1.01 day, weeks? Sorry, I keep forgetting. None of these units matter. It's okay. What's the area after 1.01 time units? I don't know why I keep writing 1 times. It doesn't matter. Does everybody kind of get the idea of what I'm trying to do? I'm stepping closer and closer to 1. I'm actually trying to figure out what's the rate of change right at 1. So trying to get closer and closer to 1. All right, stay with me. This is so cool. You got to trust me. This is a connection that was never made for me when I first learned what I'm about to teach you. So I'm hoping this will, okay. Anybody? What do I get? I haven't done this yet. What do you guys get? Sorry?
2.0139.
Yeah. 2.0139. I like it. Now let's do the same thing we did up here. What's the rate of change? It would be 2.0139 minus 2 divided by 1.01 minus 1.
1.39.
1.39. Now, let me see. This is from 1 to 1.01. Now watch this. Can't I do 1 to 1.001 a little bit quicker now? Wouldn't that be the area at 1.001 minus 2 divided by 1.001 minus 1? Is that cool? Doing the same thing here, the same thing here, the same thing here. I just want to do one more step. So now you got to figure out 2 to the 1.001 minus 2 divided by 0.001 basically. Oh shit. Let's see if you guys can handle this. Stay with me now. This is so cool. You got to stay with me. Does it seem like we're zeroing in on something? Does that make sense what I just said? Did anyone get that yet?
1.386 or 1.38.
Yeah, 1.37. Yeah. Do you see how it's kind of, I got 1.435, 1.39, and then I got 1.387. It seems to not be changing as much. So if I kept going, I'll bet you anything it's going to stay around 1.38 something. Okay, now stay with me, stay with me. This is so cool. What we're getting a feel for is how much is the area changing, not between 1 week and 2 weeks or something, but exactly at 1 week. How much is it changing right then? That's crazy. Now, stay with me, stay with me. Now, I'm going to take this away. We don't write, we don't use this form as much. Well, we do still use this form, but there's actually a more useful form for this. And that would be this form here. Why does everything have to be so hard? I know. But this should look vaguely familiar. This is like continuous growth, right? Continuous compounding. Now, all right. So stay with me. This is interesting. So watch. There's a couple of different ways. I'm going to do this the hard way, and then I'll show you the shortcut for this specific problem. So remind me, let's do some easy stuff here. What's the area after no time? Does somebody remember? So remember, this is it. So let's use this equation to get some points. and then I'll plug those points in this equation to figure out what the shit this is. Okay, now stay with, and then I'm gonna make a connection between what the hell we were doing down there to what the shit we end up with here. Okay. So what's the area after 0 seconds? I mean 0 weeks at the beginning.
1.
Sure, here. When you put a 0 in, you get 1.
1.
1 square meter. What's the area after 1 week? That's what we figured out earlier, right? 2. All right. Let's use this information to figure out the parts I need here, right? Well, this part and this part. You guys see how there's this part is called the initial amount. Whenever you see a little 0 on something, that normally means the initial something. You can think of it as O for original if you want to, but it's really 0 for naught, A naught, but it's the initial amount. So of course, what should that be? What was the initial amount? Freaking 1, right? So sure enough, if we double check, so let's take our formula and let's plug a 0 in, and we would get A0 e to the k times 0, and that's supposed to be 1. Well, what is e to the 0? What's e to the 0?
1.
1. So you do get A0 is 1, just like we said it should be. A0 is 1. So now we know this much. Okay. Now I'm gonna erase this. I need some room because I don't want to erase that. I don't want to erase that. Okay. I'm gonna erase this. And then we're gonna use our second piece of information. So if I put 1 in, that's 1 e to the k times 1, and that's supposed to equal 2. So e to the k equals 2. Don't say a word, solve that. Don't say anything, solve that for k. Solve that for k. Solve that for k, yeah. All right, now tell me, did anyone get the solution? I want the exact answer. Let's see who remembers what that means.
So is it the natural log 2 equals k?
Yeah, take the natural log of both sides, that dies. K is the natural log of 2. Now, so let me write what this equation would look like then. Let's plug in everything we know. We know that the original amount was 1. And we know k is ln 2. And we normally put the t out front so we know it's not inside the ln. Do you see what I'm talking about? So we put the little t out front. Might be too small. I've written very tiny here. I'm sorry. Now watch. This is so cool. Now somebody tell me, what is natural log of 2 approximately equal to? Please.
.693.
0.693. Now, here's the cool part. How do I connect this for you guys? Yeah. Remember this one, the way we got there? I should have started with 0. I knew I should have, but let's see if you guys can go with me. This is the percentage that is applied to this to get to the next instantaneous place. So the shortcut is, what is this times 2? What is 0.693 times 2?
0.39. 1.39.
Go further. Is it 1.3?
1.386.
Which is what this looks like it was going towards, correct? Yes? I knew I should have picked 0, but that's too bad, Jeff. Hopefully you guys are with me. So there's not a damn thing wrong with this equation. It's just that when I write it in this form, I've lost the form now, Jeff. Good job, buddy. When I write it in this form, the K represents the instantaneous percentage of the amount I have now that will be added to it for the next step, for the instantaneous next step, not 1.01, not 1.001, but right after 1. 1.001, right? I don't know if you guys are with me at all. Please be with me a little bit. I really want, so this is what I did not understand when I was first, I don't blame you, Bowen. When I was first shown this, doesn't this look much prettier than this? They are the same, by the way. I'm going to prove that in a minute. These are the same equation, but doesn't that look prettier than this? Of course that looks prettier than that. Of course it does, right? But this shows me, I really want you guys to understand, think about this. If something doubles in height, when it starts at 2, doubles in height every year. After 1 year, how tall will it be if it starts at 2?
It'd be 4.
Yeah, 2 times 2. Half a year. It would be
3.
2 times a half of 2. 2 times the square root of 2. Are you guys kind of with me?
Oh,
So-
yeah. Okay.
And how long can I keep cutting? I really want you guys with me. Don't worry. I'll get there in a minute. Don't worry. Stay with me now. So if it started at 2 and it doubles every year, after a year before, after half a year, it'd be 2 times 2 to the 1/2, 2 times square root of 2. Couldn't I keep cutting it in half, cutting it in half? So at this year's 2, wait a month. No. Wait a day. No. Wait a minute. No. Wait a second. No. Wait a millisecond. No. Wait 1/10 to the billion seconds. No. Wait, do you guys understand? I'm cutting time more and more. And each time I do that, I can figure out what percentage it increases by. K is the percentage it increases at the smallest possible chopping down of time. It's so flipping cool. And look, we only chopped it down to 1.001, and we still got really close to what it would be. So you don't have to go that far. All right, now Bowen, which one are you talking about? This one?
Yes.
That's because I set the problem up where it started at 1 square meter. So the original area of the spill was 1 square meter, so that's why that's a 1. And we did the work. I erased it down here, but we did the work here. That was what was here before. All right. So I'm really sorry. I knew it was going to be trippy to try to make the connection, but at least I really want you to understand there's a actual physical purpose to why this is preferred to this. Now, I'm going to erase this. Let's get past this. The main thing I want you to get from this is that K has a physical interpretation. It's not just some made up bullshit to make things harder. Okay. All right. So let me erase this. Now I want to show you, I want to prove to you that this equation and this equation are the same. Right? I want to prove to you those are the same. So let me see. How do I do that? I'm going to start with this guy. Let me rewrite him a little bit. So pretty cool. Now watch this. You ready? You got to be ready for this. Well, there's a shorter way to do this. What can I do with that t? Using a property of logarithms. What can I do with that t?
That's an exponent.
Sure. So what can I do with it?
Move to the 2.
You guys remember that? Is that cool? If there's a power inside the log, it can take it down. So of course I could put it back up. Math goes both ways. Be jealous. Okay. Some of you guys got it. What happens here?
They die.
They die. So I get that. Yeah, they're the same thing. Now watch what comes out of that. Let me stop for a minute. I really want you guys to all realize that they are the same thing. So this is just a different way to give the same formula. It has information. This means something. That's the thing. Even if you don't quite get from my whole oil spill business exactly what it really means, it does have a physical interpretation. So there is a reason for writing things in this form. Now watch this. This is a cool little outcome to what we just talked about. If I have the number 7, I can write that as e to the natural log of 7. Do you guys see that? That seems stupid, right? To some degree. Why would you ever do that? If you go far enough in mathematics, which is not very far from now, this exact thing will save you on a few kind of problems you have to do. Knowing how to rewrite anything in exponential form like this. Just a poor little 7 just sitting there. Look what I did to it. Ha! I mean, it's pretty cool with the fact those are the same, of course, right? Okay, so that seems kind of arbitrary, like, okay, 2 is 1 plus 1. Great. So, but this has a real purpose. Okay. And it sort of goes along with what we just did. All right, so let's bring it all in. Let's talk about what we're going to have to be able to do. Let me write down. So this is the big bad equation that we're going to use. I don't like the way the book does this, but what do you think would change? So this is exponential growth. What would change if it was exponential decay, like radioactivity? What would be different? So why is this exponential growth? I'm assuming k is greater than 0 because then it would be like this. What would make it change to be this for decay?
Would it be like 1 over KT or?
No.
Oh, okay.
K is smaller than 0.
Yeah, or do this. Now, personally, I agree with what you just said, Rio. I'd rather say k greater than 0 and k less than 0, but I think the book puts a specific negative on there, if I remember correctly. Okay, so this would be in your face growth, and that would be in your face decay. Okay, maybe. Because this is a reflection around the y-axis, and that's what this accomplishes. When I put a negative next to the variable, it's a reflection around the y-axis. Or in this case, the a-axis. So let's do a problem. What's unfortunate is a lot of the problems you're going to be asked to do are not going to be continuous problems. I want you to remember, to realize that doesn't matter. This equation will still work. It will still model for things that are not continuous. It's just when I get decimal answers, I round them. So it's not perfect for discrete kind of data. Discrete means 1, 2, 3, 4, you know. So continuous would take on all the values. Okay, so for example, if I had bacteria, and what do bacteria love to do? They love to
Multiply.
Oh, okay. Something weird was happening outside. All right. They like to multiply. They like to make more and more and more bacteria. So let's say that at the beginning, at t equals 0, there was 4,000 bacteria, 4,000 bacteria. Yeah, it'd be. And at t equal to 3 minutes, there was 12,000 bacteria. Okay, now, if you have some faith in yourself, you should totally be able to figure out what the equation is for this situation. Go. I'll stand here and wait. Figure out what the equation is that models the growth of this bacteria, assuming the rate stays the same. Oh, man. Let's see what can I do. Yeah, we can do that. I really want to get a little bit of trig in tonight before you leave. We'll see. Can somebody, do I have to do any work to figure out what A0 is, A naught? If you remember what A naught means, the initial amount, what is A naught?
4,000.
Yeah. So you only have to use both points, like plug it in if that's not 0, right? Because then they didn't tell you the original amount, those bastards. But here I did. I'm nice. So this is A0. So from this one, I know A0 is 4,000. So now I can write holy crap. And now I can use this information to help me figure out the only remaining parameter, which is the K. So let's see. Let me catch up to you guys. So after 3 minutes, so I put a 3 in here, I should get 12,000. So now I just got to solve that for K. So what do you guys get for K?
Three.
No, you get, so if you divide by 4,000, you get e to the 3k equals 3. Keep going. You got to solve for k. You put it over here.
0.366.
Give me the exact answer. Is everybody cool with what's happening over here? So that's what k is, right? So another way you can say this is every 3 minutes, what does it seem like it does? Every 3 minutes,
It triples.
triples. Okay, I like it. So this is kind of neat that there's so many, of course, there's so many 3s because it's built on 3 minutes and it triples. That's kind of like where all the 3s are coming from. Now, what does this formula look like now? And I've got all my parts that I know now. Area. The amount of bacteria at a certain time is 4,000 e to the t ln 3 divided by 3. So how much bacteria will there be after 2 hours? Will you put a 2 in there?
No.
Hell no, it's in minutes. 2 would be 2 minutes. Right, so that's another level you got to be careful about with these problems. It's not that big of a deal. Just make sure you're plugging in numbers that make sense with the units they give you. So what am I going to plug into A?
40. Sorry, no. I was thinking every one was 3. 120.
Don't overthink it. Yeah, I just need to know number of minutes. 120 for 2 hours, right? So 120. Natural log of 3 divided by 3. I could do this before I plug it in the calculator. I can plug all that shit in the calculator. You're going to get a lot. It's going to be a very big number. So this is why you don't want to step away from the lab for a couple hours. Holy shit. So did anybody, oh, I'm sorry. 2 hours. Time is in minutes. So 2 hours would be 2 times 60, 120 minutes. So you got to be really careful about the time that they set things up with. So we built this equation based on minutes. So the only thing it understands is an input of minutes. I like it. We could have built it based on hours. We totally could have. I would have had to put 3 over 60 hours anyway, so that would have been kind of gross. Anybody get the answer? Can you interpret what your calculator says? All right, you can show it to me, but can you interpret it for me? Blah, blah, blah. What does E mean in your calculator? What does E mean?
Number of zeros.
Sort of. So times 10 to the 22. So it's moved the decimal place 22 times to the right. That is insane, right? That shouldn't surprise us after the pennies problem. This one's tripling every 3 minutes, so it's more than doubling every day. I mean, that's crazy. Okay, maybe. There's a lot of bacteria, dude. Your whole place, I'm sorry, it's covered in bacteria. All right. Let me see. All right, how much time we got? Not much. So I really want you to notice something. They do this in a lot of problems. This is a very classic problem. They give you 2 pieces of information so you can figure out A naught and K, and then they ask you, like I did, all right, what about 2 hours later? Okay, and then you just got to throw it into the equation that you just created. All right, I like it. Now, yeah, let's try to do Newton's law. Okay, leave that up there for a minute. Pull up the book. Let me see if I can take myself out of the equation. Okay. Let me show you this. I think everybody should be done copying stuff, right? Now, if any of you do take calculus, by the way, I am teaching both 178 and 180 next semester. I managed to get both of those, which is nice. So if you want to avoid me, there will be plenty of other people teaching those courses, but I will be teaching both of them if you want. Here, this is what I'm trying to do.
Do you have any idea when we're supposed to go back to campus?
No.
Darn.
Didn't I talk to you guys a little bit about, it's kind of funny. I'm involved in some of the district plans and they've called it the repopulation team. And I was like, can we call it something different? Because that sounds like we're trying to, it's an apocalyptic thing. And we got 4 guys and 5 women. We're like, all right, we need to make some more humans. So I don't know, remember they're throwing around some names. I'm like, it's not as important the name. Anyway, nobody knows. They don't want to make a determination yet, which I don't blame them. But then we're kind of planning like halfway. Maybe we can go back, maybe we can't, maybe we can go back a little bit, maybe we can go back like the stupid way that some schools are doing it, K through 12, where one day you're in classroom and the other day you're on Zoom. I mean, I don't know if that would be, I think that would be better, but it would also be a little insane for trying to cobble together a schedule. Anyway, so right now, no flipping clue, dude. 178 and 180, yes. And I'm teaching a 160 and maybe a 120 if I don't get a position that I applied for. All right. If I get the position, I'm going to drop my 120 because then that would be too much. All right, so watch this. This is Newton's law of cooling. This should look very familiar. What do I mean by familiar? Well, that piece definitely looks familiar, correct? Crap. Go away. All right. So what do these things mean? So here's how this works. This is the temperature of the surroundings, right? And I think they tell you that somewhere. Oh, down here. Okay. Well, let's see. All right. Surrounding air. Okay. So the temperature of the environment. So let's say you have something you take out of the fridge and it's a certain temperature and you put it down in a room that's 70 degrees, right? So then you can ask something like, well, how long until the temperature of that, let's say it's a Coke. I take a Coke out of the fridge, put it on the counter. How long until that Coke is a certain temperature, right? Is everybody kind of with me, you guys? Or it could be the other way around.
Or how fast your hot tea becomes cold.
Exactly. I heat up some hot tea. I put it on the counter. I forget all about it. I come back to it later. I'm like, poor little tea. How long until it's whatever temperature, right? So obviously what's going to happen is that it's going to work towards equilibrium. And technically both temperatures change a little bit, but you're talking about a huge room versus a little thing of tea. It's just like if you drop an orange to the earth, the orange attracts the earth as much as the earth attracts the orange. Have you ever heard that truth? It's just that the earth is so massive, the amount it moves is negligible. All right. Anyway, so that kind of freaks you out the first time you hear that. All right, but think about that. Anytime you drop something toward the earth, you're pulling the earth up. Just not very much. Okay. The A here is the difference between the initial temperature of the object and the surroundings. So, for example, I knew I should have set this up the other way. I don't think I'm going to get my wish to look at some angles, but that's too bad. Hold on, guys. Let me move this to the other screen so I can do this shit. Bam. Bam. So I want this to make some good sense here. All right, now watch this. If I rearrange stuff in this equation, it's going to make a little more sense is my hope. So if I do this, so this is the temperature at some time. If I subtract this, I really want you to understand. So A is the initial difference, right? Let me reword what they said. It's the initial difference between what you just took out of the fridge or just took off the stove and the room it's in. And that is proportional to the difference at some time t. So that difference is going to kind of get smaller and smaller by some percentage. And guess which piece of this deals with the percentage change that it takes? How many people were paying attention earlier? Which piece of this equation deals with that percentage?
The K.
Yeah, the K. Sorry, I gave a little clue. All right. Remember, that's what I was saying earlier, that K is related to the rate at which things change. It's the instantaneous rate, but that's not that important. All right, maybe. So let's do a concrete example, right? You guys are like, give me some freaking numbers, please. All right. So let's say the room is 70 degrees. That's Fahrenheit. And I have some soup that is, I don't know, what makes sense? I have no idea. It was just boiling, so we'll say 170 degrees Fahrenheit, right? I take it off the burner. I put it on a little hot pad, whatever the hell you call those things. And let me see, I have to give us this. So normally we have to figure out what K is, but let me give you what K is. Let's say K is, let's see. Oh, this is, I should have taken this. Let's hold on, guys. Let me take a problem out of the homework, or else I'm going to just make some weird shit happen. Hold on. Let me see if the homework has a soup problem. Where's Newton's law? There's some Half-Life stuff. I like it. Here we go. All right, let's do this. Beautiful, beautiful. Pot of, oh, the soup. Oh my God. Sorry. Pot of soup, 100 degrees Fahrenheit. They should really boil that thing. What the hell? Take it off the stove. And look at this. It's almost the same. 69-degree Fahrenheit room. All right, after 15 minutes, the soup is now cooled to 95. It, of course, is approaching the temperature of the room. So let's identify the parts here. Let me rewrite the equation. So we got T, the temperature at some time is, I'm trying to remember the symbols they used. Okay. All right, so what is TS?
69 degrees Fahrenheit.
Good, 69 degrees. What is A? A is a little bit freaky. I don't know if you guys remember what I said A was. Go ahead.
It's
31.
the initial difference, right?
The initial difference, I love it.
31.
31. All right. What else do I know?
15 minutes.
Yes, good. So I know that at T equal to 15, the temperature of the soup was 95 degrees. So that would be T of 15 is 95. So this is the temperature of the object or the stuff, the soup in this case. This is the temperature of the surroundings. And this guy is how different those are. So think about it. Why does that make sense? The rate at how quickly something cools should be directly related to how different the temperatures are, right? If I put something in the freezer, it's going to cool down faster than if I put it in the fridge because the difference in temperature is so great between the two things. So the rate of cooling would be quicker. All right, so let's plug in all the shit. What do I have to figure out that I was going to give us earlier, but now I don't have to. I can make you guys figure it out. K is the big, bad, important boy. Why can I figure it out? Because now I have initial and I have after so many minutes information. So I'm going to put T of 15. So 95, that equals A. Well, we know what A is. Get out of there, A. Let's plug in everything we know. 31. E to the K times 15 plus 69. All right, so take a minute and figure out what K is. Shit, why can't I pull it? There you are. I'm not going to do that. Get away. Let me see. And I want the exact answer first. That's all right. I won't do any degree stuff tonight. So watch this. If I start to do this, I have to subtract 69, right? So I get 26, and then I have to divide by 31. Then I have to take a natural log, and then I have to divide that by 15. Whoo! So subtract, divide by 31, take a natural log, and then divide by 15. So that's what K is officially in its full, glorious form. How long will it take the soup to cool to 80 degrees? What would I do for that? Let me write down what we have for the formula now. got mesmerized by me erasing stuff. Okay. So I have T of T equals, that was good, Jeff. You just erased important information. You can remember 31 e to the this business times T plus, where'd it go?
69.
So how long will it take to cool to 80? So now I know the output will be 80, and I'm trying to solve for T. Now watch what I could do. Let me show you. I'm not going to do all this. This is going to feel very familiar to some of you guys. I don't want to write all that, do I? So guess what I'm going to do? I'm going to write frickin' K. And then later I can throw in what K is. That kind of feels like that substitution thing we were doing before when I don't want to write all this shit down, right? So now I just try to solve for T. So I got to subtract 69. I get 11, divide by 31. Is that cool? Subtract 69, divide by 31. Take the natural log. And then divide by K. So this would be an exciting thing. Let me see how you guys, if you could plug this in your calculator. All right, sorry. I'm laughing so evilly. I love it. So natural log of 11 divided by 31. So what I'm going to do is I'm going to divide by parentheses, put in there what K is. 26 divided by, Jeff, you could do it, buddy. Divided by 31. Divided by 15. So let me show you what I'm doing. This is a really easy problem to screw up. How can I do this without, has everybody got all this copied down? Anybody? All right, I'm going to stop sharing, see if anybody cries. Okay. All right, nobody cried. Good. I couldn't handle that. Somebody's crying. There's no crying. There's no crying in math class. All right. So here's what I plugged in. Right? Parentheses. This whole thing in parentheses is K. All right, let's see what we get. Let's see if it makes sense. After 15 minutes, it cooled down by 5 degrees, right? So to get down to 80 is another 15. So it takes 88 minutes. And the thing to realize, now real quick, stay with me, stay with me. Didn't it, it took, let's see if I can remember. It took 15 minutes. Where'd it go? 15 minutes to cool 5 degrees, right? Now you could say to yourself, if it took 15 minutes to cool 5 degrees, you might think that it would take 45 more minutes to cool another 15 degrees. Do you guys see how I got that? And it's actually wrong. I really want you to understand the reasoning behind what I just did and why it's wrong. So if it took 15 minutes to cool down 5 degrees, you could kind of naively think it would take 3 times as long to cool down 3 times as much.
Right, but it cools less and less.
Say again?
It cools less and less
The
between
rate
each
at
interval.
which it's cooling is going down every time the temperatures get closer. So it's taking longer and longer and longer and longer to cool down another 5 degrees. So that's why it's not an hour. It's actually almost an hour and a half.
Is it exponent decay?
Yeah, exponential decay. Yeah. And this is because it's so it's not decay in that sense. The time needed is growing, but the rate at which the temperature is dropping is kind of like exponentially decreasing in a way. Not really, but okay. Whew. All right. Let's see, how much time do I officially have? Like nothing. That's fine. All right. I'm going to do one thing. I have to do one thing. All right. So most of the problems in that section are going to be related to the problems we just did, the soup problem and the bacteria problem. Before I let you go, how many degrees are in a circle?
360.
360.
360. Did it have to be 360? Is there something special about 360?
Isn't it just the smallest degree to make a complete circle?
All right, I kind of know what you mean by that, but did the number 360, did it have to be that? This is a very interesting question because this is something you guys feel is a foundational thing, but it isn't. I'll just tell you. There is a reason mathematically you like 360 because it can be broken up in many ways. How many factors of 360 are there? A ton. Which is why I think I told you the Babylonians had a number system based on 60, right? Because they like to break things down in terms of the year, which they approximated to be 360. Why was that important? Because harvest, holy shit, which basically meant everything because that's back when it was hard to get food, right? Unfortunately, it's still hard to get food for some people nowadays, but it's a little easier in general. So the main thing to get from this when I'm spewing at you is that the number 360 doesn't mean shit. We could have made it 400 degrees. We could have made it 2 degrees. It totally, completely arbitrary. Are you guys understanding? It really was. It's really a cool, was it the Sumerians? I don't know. You might want to have to Google this. Where did 360 come from? I think it was the Sumerians who broke it down based on the year, based on the length of the year. They broke it down. Stay with me. I know. There's a better unit that actually has a physical meaning. Degrees do not have a physical meaning. They don't. There's a better unit of measurement for angles in a circle. And it's based on, hey, look at that. Somebody's ahead of me. You guys can't see it. Somebody private messaged me. Can you tell me what that means, what you just wrote? So has anybody ever heard of a different unit of measurement for degrees? I know at least one person has. Has anybody ever heard of, no, I like that. It's related to pi. It's very much related to pi, but it's not pi. So here, all right, this is, I don't want to do a lot, but it's based on the length of the radius. So one thing I'll tell you is this, if I take any circle and I take its radius, right? I take the radius, take it out and I curve it and I fit it on the circle. So here's the radius. You with me? So I bent the radius and I put it on the circle. You with me? That is 1 radian. That is why we call it a radian, because it's 1 radius of length along the circle. That's so beautiful. So it has a physical meaning. It's the length of 1 radius along the circle. Degrees are made up bullshit. Radians are physical. They come from the circle. And if I made the circle smaller, it goes to the exact same angle because the radius got smaller. So it's going to fill the same relative amount of the circle on the side. It's going to be the exact same angle. What? And they're called radians. And so the first thing we're going to have to do is figure out how to convert between radians and the made up bullshit degrees. It's sort of like converting between centimeters and inches, right? Centimeters, which are the better unit, and inches are the bullshit unit, but oh well. We're lucky. We live in America. Yeah, go us. All right, sorry. That's enough, guys. That's enough. Yeah, unit circle stuff is coming up. It's really some cool shit. We're going to talk about sine waves and all that kind of stuff, and yeah, talk about plucking guitar strings and the frequencies and yeah, buddy.
What is the difference between radian and radius?
Was pretty much what I just said. So the radius determines what 1 radian on a circle is. And the really cool thing is, I don't care how big or small your circle is, it would go through the same angle in the circle. If I can draw a better picture. So if I had a circle, can you guys see? No. All right, Jeff, pick a better marker. Hold on. I'm not one of those people I can go, whoa. All right, if I had a circle, and I took its radius, and I curved it, and I put it there, that would be 1 radian. If I had a smaller circle, same angle. Radius, curve it, same angle. So we are going to take a circle of radius 1, and we're going to base everything on it because it will scale up. It scales up beautifully. It's too nice. So next time we'll talk about what's the connection between pi and degrees and radians. I'll show you a video that tells you where pi came from, how they used to estimate pi way back in the like 1600s and stuff. They're like, why would we want to know that? Come on, some cool shit. All right, it's related to this actually. Sorry, that's the holy grail of equations. You tell this to any math person, they'll get a little like, oh. Yeah, sorry. All right, that's enough. All right, guys. So the quiz is open. You can go start it now if you want to. It's not due until tomorrow at 9. So you should have some time somewhere to do it. I think I gave you an hour and a half to do it. So it should be plenty of time. 9 p.m. 9 p.m. I definitely would not make it to 9 a.m. That would be so evil. So it's due tomorrow at 9 p.m.
Do people with accommodations already have the time?
Oh, thank you. All right. Yeah. So I can go build that in right now. I've got my list of the people. Thank you for reminding me. You got to do that for me. Yes. So I can go do that right now. So don't open it yet. All right, guys. Let me know if anybody has any questions. Otherwise, you're free to go.
Thanks, Prof.
You're welcome, Stude. All right, let me see.
Thank you.
No worries. You're welcome.
Have a good night.
You too. All right, let me see. All right, I'm out of here, guys. If anybody's out there. Bye.